And we continue. Acids and bases. This is one of those areas that is critical to understand because, as you will see in just a few slides, there's going to be some diseases that are related directly to acids and bases. Let's look at some focus questions here. What makes a chemical an acid or a base? What are some examples in the body? What's the pH scale represent? And what do buffers do? And why are they so important in the body? Let's look. Let me move me. When we talk about something as an acid, it is something that generates or produces hydrogen ions when dissolved in water. An hydrogen ion is just really a proton. If you recall back what hydrogen was, let me grab a pencil. Hydrogen is going to be H with one proton, and it's going to have one electron. If it forms an ion, and all it is, and by forming an ion, I mean it loses what? It loses an electron. Then really all a hydrogen ion is a proton. So you might have not have cared about that, but I thought I'd share it anyway. So hydrochloric acid, when you put hydrochloric acid in water, it forms hydrogen ions, protons, and chlorine. And you can see that in our example here. This represents chlorine. This represents hydrogen ions. So when you put hydrochloric acid in water, it forms an acid. That is, it generates hydrogen ions, and therefore, by definition, it is an acid. Some examples in the body. We do see hydrochloric acid in our stomach, and we'll discuss that in AMP2. Acetic acid is an important step in our breakdown of alcohol. Carbonic acid is going to be related to, or in part connected to, our blood metabolism. Bases do the opposite. They do not release protons, they take them up. Sodium hydroxide, NaOH, is going to, when you put NaOH in water, it forms two things. It forms sodium ions, and it forms hydroxide ions, OH negative. The OH negative, of course, when these are around, is going to then soak up, take up any of the hydrogen ions, and therefore form water, and that makes it a base. You'll often see OH negative connected to most bases. That OH negative is going to be an easy way to grab hydrogen ions, form water, and therefore that makes them a base. Some examples: HCO3, bicarbonate ion, and ammonia are examples of bases in the body. So what's the pH scale? When we talk about the pH scale, what are we talking about? We are talking about the relative concentration of hydrogen ions and hydroxide ions in solution. Look at this little chart here. If you have lots of hydrogen ions here, since hydrogen ions are going to be the product of acids, this would make this an acidic solution, lots of protons. A solution that's not acidic, that's actually basic or alkaline, would have relatively few hydrogen ions and would have more hydroxide ions in this case, so OH negative. So when we look at the pH scale, this scale represents a relative concentration of hydrogen ions and hydroxide ions in solution. If we had a pH of 7, which we call neutral pH, like in distilled water, that means we have an even number of these. This is not acid or base, it's neutral. It's right in the middle. If I start going this direction on the pH scale, that means I'm going to start tipping the balance toward having a few more hydrogen ions in solution than hydroxide ions. So if I'm pretty close to here, I'm going to call that a relatively weak acid. It's acid because it's above 7. That is, it's more concentrated than pH of 7, and we'll discuss the numbers in a moment. As I move this direction more, I'm going to have even more hydrogen ions relative to hydroxide ions, and this is going to be a stronger base. And then if I'm way up here at the top, If I get to a pH that I would call, for example, 2 or 1, it's a very strong acid because I have a lot of hydrogen ions. Now I'm being a little silly, but a lot of hydrogen ions relative to the other ones. That would make this a strong acid. Likewise, if I move this direction on the pH scale, I would have a few more hydroxide ions, and therefore I would call it basic. If I keep moving this direction even more, all the way down to the end where I'm at pH 14, that would be a very strong base because I'd have a lot of those, more like this case here, a lot of hydroxide ions and very few hydrogen ions. So when we refer to pH, we're talking about a number, 7 or 5 or 10. It actually, and maybe this is more detail than you want to know, but it's actually referring to the negative log of, that's like a G, of the hydrogen ion concentration. So it really represents a number of hydrogen ions in solution. So at 10 to the negative 7, or pH of 7, that refers to a certain concentration. But if I go 6 to 5 to 4 to 3, since it's a negative log, that means it's actually becoming more concentrated, and that means there's actually even a higher concentration of hydrogen ions. That's what makes this more acidic. This is what makes this direction more basic. A pH of 7 to a pH of 8 is going to be 10 times less hydrogen ions. From 7 to 9 is 100 times less hydrogen ions because it's a negative log scale. All you really need to know is as the pH goes from 7 to 0 or from 7 to 14, it's either getting more acidic or more basic. You'll notice on our scale next to it some common biologics here. You see the pH of blood is going to be 7.4. The pH of urine can range from 5 to 8. Coffee is about 5. Tomato juice is about 4. So as you go, again, that direction, it's going to become slightly more acidic. As you move this direction, again, it's going to become more basic. So the pH scale is important because it tells us something about the number of hydrogen ions and hydroxide ions in solution. Okay. This chart just gives us that same idea. It just shows us what we refer to as the pH scale. And just to reemphasize one more time, pH of 7 is neutral. As you move this direction, it's weakly acidic. That is, it's still more hydrogen ions. But as you move all the way down here, it becomes strongly acidic. Weakly alkaline or basic is moving this direction. If the pH is of over 7 up to 14, it's considered basic. But way on this end of the scale, it's very alkaline or very basic. So what, who cares? Okay, why does the pH matter at all? Why do we have to know this stuff? Because this can directly affect metabolism. A condition known as acidosis is when the pH of the body fluids, particularly the blood, drops below 7.35. Okay, so remember the normal pH of blood is about 7.4. So if you have a pH drop of 7.35, that can be caused by asthma, emphysema, ingesting acids. Several other conditions can cause this. The pH will drop below 7.4, below 7.35. It's becoming more acid-like, even though it's still technically at the basic pH. It's becoming more and more acid because the pH is dropping. It's getting smaller. This will depress the central nervous system, eventually cause the person to become disoriented and possibly comatose, and it can be fatal. Flip side, there are conditions like hyperventilation, ingesting large amounts of sodium bicarbonate. Some drugs will do this. If there is too much acid be eliminated from the blood, from the kidneys, the pH will rise and it'll become alkaline. And this is alkalosis. A pH is 7.45 or above is considered alkalosis. This is hyperexcites the central nervous system, which causes spasms, nervousness, and convulsions. And this can be fatal. And you're thinking to yourself, if it's 7.4 and it just goes just a little bit to 7.35 or a little bit to 7.45, that can lead us to some possibly fatal conditions? Yes. That's why it's really, really, really important that the body has a mechanism of maintaining and protecting its pH at all times. A buffer are Buffers are proteins or other molecules that prevent large changes in pH. They either release or absorb hydrogen ions so that the pH doesn't change very much. A buffer kind of goes both directions. A buffer can, in this case, let me grab my pen, a buffer in this case is holding hydrogen ions, but if the pH was to change and it was becoming a little bit too alkaline, too basic, it can release a hydrogen ion and therefore keep the pH from getting too basic. Same time, if the pH was getting too acidic, the buffer can grab the hydrogen ion, hang onto it, and therefore take it out of solution, and the pH there will actually become less acidic because you removed this from solution. This is one of the more famous examples. This is the carbonic acid bicarbonate buffer system, which regulates the pH of blood. Here you see CO2 and water. This double arrow means it's a reversible reaction. This is carbonic acid. This is the bicarbonate ion, and of course we recognize our hydrogen ion here. If the body was, for example, through some mechanism becoming more acidic, then more hydrogen ions would bind to the bicarbonate ion and form carbonic acid, and therefore take hydrogen ions out of solution. If you combine this mechanism with other mechanisms the body has, like breathing, you can get rid of extra acid from your blood very quickly by the whole reaction shifting to the left. Likewise, if you have CO2 and water, can actually form then carbonic acid, which allows the body to carry CO2 in the body in a little different form. We'll spend more time on this in A&P2, but I wanted you to see that buffers are vital for maintaining homeostasis. If you do not correctly maintain homeostasis, then we have a term for that in biology. We call that dead.